going to cover section 3.2 of our BJU Press Pre-Calculus textbook. We're going to be looking at exponential functions. So we're going to identify exponential functions, classify them as either growth or decay, and then we're going to evaluate and graph them. We're also going to apply exponential growth to compound interest. So which would you rather have? Would you rather have $100,000 a day for 30 days? Or would you rather have 1 cent on the first day and then on each succeeding day double the amount of the previous day? So looking at these two options, option 1 looks pretty good from the start. Plan 1, if you have 30 days and you get $100,000 each day, that is a lot of money. We're talking about $3 million. Plan 2 takes some work to calculate. On day 1, you just get your 1 penny, right? On day 2, you get double that, so you have 2 pennies. On day 3, you get double that, so that means you have 4 pennies. On day 4, you double that, and you get 8 pennies. So notice how the doubling that I'm doing with exponents, right? So I start with 1. Double of 1 is 2. Double of 2 is 4. Double of 4 is 8. So with exponents, I start with 2 to the 0, 2 to the first, 2 to the second, 2 cubed, and that makes it 2 for every day I'm doubling. So I keep going, and on day 6, I'm up to 32 cents. And I keep going. Day 10, I'm finally at $5. Let's jump to day 15, right? So if you've noticed, for every day, my exponent is just 1 less than the day that I'm on. So if I'm on day 15, that means my exponent is 14. That means I've doubled 14 times. And I'm finally at $163.84. That's halfway through. Do I really think that I'm going to get more than $3 million at the end of 30 days? Let's keep going. At 20 days, I'm at $5,242.88. And then this just shows me my formula. Depending on what day I want, I just subtract 1 from that, and that's how many times I double, right? So if I want 30 days, I'm going to do 2 to the 29th, and then times 1 cent. Oh, and I get $5,368,709.12. So I do end up getting a little bit more money that way. So if we are looking at f of x equals x to the 4th, that's an example of what we studied in the previous lesson. It is a power function. However, if we are going to move this variable and our variable moves to the exponent part, right? So our variable is an exponent. That means we have an exponential function. So again, when your variable is in the exponent spot, you have an exponential function. So it has the form of this, c times a to the x, where c and a are real numbers, and c has to be bigger than 0, and a has to be bigger than 0, and a cannot be equal to 1. So let's look at a general graph. We're going to graph 3 times 2 to the x power. So we can plot some points. We can also plug it into our graphing calculator and get a rough sketch. And it looks like this. So our domain ends up being all real numbers because there's no limitation on our x values. But if we're looking at our range has to be bigger than 0, right? Because we are not going to have any negative y values. So we saw that our a value had to be bigger than 0. However, our a value cannot be equal to 1. That doesn't mean that a has to be bigger than 1. You can still have an a value that's a fraction where it's between 0 and 1. When you have something like that, though, because it is a fraction that you are either doubling or you're taking to a higher power, your number is actually going to get smaller. So when you have an a value that's between 0 and 1, your y is going to decrease instead of increase. And so we call those our decay functions. If your a is bigger than 0, then that's when you have your exponential growth function. So let's look at an example of a decay function. So look at this. You have 1/2 for your a value. So 1/2 is what we are going to take to a higher power. So that means that every time we plug in a number, we're going to get a smaller and smaller y value. And when we graph that, our graph is going to go downwards. Okay, so notice that exponential functions have no zeros. They never cross the x-axis. They get really close but never touch it. And we call that a horizontal asymptote. So let's look at some examples. Let's say we have a bank that offers 5% annual interest compounded annually. And then we have another bank that offers 4.9 compounded, but instead of compounding annually, it's going to compound monthly. Which bank is going to pay more if we start with the same amount? We're going to start both banks with $300, and we're going to invest for 10 years for both of them, but we want to know who's going to make us the most money, the one that compounds annually or the one that compounds monthly. So we first have to remember our formula. For an annual compound, we have P times 1 plus R to the T power, where P is our principal amount, R is our rate, and T is the time in years. So if we have 10 years, that's going to be 300 times 1 plus 0.05, because that's our rate by percent, times 10 to the 10th power, which is the 10 years. So that is $488.67. So that's what Bank A makes us after 10 years for $300 at 5% annual interest. So let's look at Bank B. Bank B is compounded monthly. So that's going to look a little different. We have this N value, and N is the number of divisions in the year. So if we're doing monthly, that means that our N is 12 instead of 1. And so our formula looks like this: 300 times 1 plus 0.049, which is the 4.9%, divided by 12, which is the number of divisions in the year, to the 12, a number of divisions in a year, times 10, which is the number of years, or T. So that in our calculator ends up being 489.21. So Bank B made us more money even though it was less percent, but because it was compounded more frequently, it made more money for us. Let's do another example like that. So let's say Bank A offers 3% annual and Bank B offers 2.9% compounded quarterly, which means 4 times a year. How much more will Bank A pay than Bank B? So Bank A is annual, so we have just our plain formula. And Bank B is not yearly, so it's quarterly. So that means we have to divide our rate by the number of divisions in a year. So if it's quarterly, that means that's going to be 4 for our N value. So Bank A, we end up with $231.85. And Bank B, we end up with $231.09 cents. So just a slight difference between Bank A and Bank B. So Bank A will pay 76 cents more, even though it had a higher percent than Bank B. Okay, Now let's talk about natural exponential function. This is in the form of f of x equals e to the x power. So e, which we call Euler's number, is approximately 2.718288182, and it just repeats like it's one of those irrational numbers. It is a number that is used so often that you can actually find it on your calculator. You'll see that it says e to the, and then you can plug in what power you want. You can graph this in your calculator if you go to y equals and put e to the x. You can also evaluate it. You just in your main calculator screen you put e to the, and then you put in what number you want for your exponent. So where does this come from? Well, it comes from the infinite series shown below. So you have 1 plus 1 over 1 plus 1 over 1 times 2 plus 1 over 1 times 2 times 3. So that keeps going on and on and on and on, and that's what e is equal to. When we get later in pre-cal, we're going to learn infinite series, and it's going to look like this, where you have an exclamation point, and so we'll see what that looks like. But notice how we're doing 1 plus 1 plus 1 half plus 1 sixth plus 1 over 24. So these numbers here are really, really small, so it's not going to get any bigger than 2. However, it is going to be an actual number. So I said this before, e is also called Euler's number, and it can also be represented or defined as a limit as n approaches infinity of 1 plus 1 over n to the nth power. So let's look at what the graph of f of x equals e to the x is. I always like to plug in 0 whenever I'm doing exponential functions, because this is why. Anytime you take anything to the 0 power, your answer is always 1. So I will know if it's an exponential function, I will always have a point at 0, 1, always, no matter what exponential function I choose to graph. All right, so I plug in those values, and I sketch that graph, and it looks like this. What about if we have negative 2 to the negative x power plus 3, and we want to evaluate it from these points, and we want to graph it and give its domain and range. So I can plug in those values and find my y values. I can also plug in this into y equals on my graphing calculator and get this sketch. So if we're looking at our domain and range, there's no limitations on our domain, but there was a limitation on our range. Our range had to be bigger than 0. If we put a negative here, look what it did to our graph. It flipped our graph. And now that our graph is flipped, that is going to change our range. Our domain is still all real numbers. However, now our range are all the numbers that are less than 0. Notice how this also changed because it changed it by going, it used to be, here is your point, but because we had this plus 3, it went up 3. 1, 2, 3. So it translated our graph up 3. All right, one more formula that I want to share with you is continuous compounded interest. So we looked at some formulas where it compounded yearly, it compounded monthly, it compounded quarterly. However, let's say a bank said, you know what, we're going to do even better. We're going to continuously compound all of the time. So not just daily, not just hourly, but all of the time. Well, there's a formula for that. We call it the continuously compounded interest formula. And that is A equals P times E to the RT, where P is our principal amount. E is, of course, Euler's number, which is found on our calculator. R is the rate, and T is the time in years. So here's the thing about continuously compounded interest. It's hypothetical because it's impossible. It's not physically possible to continuously doing this. Because even if you said, oh, you know what, we'll compound it every second. Well, what about every half second or whatever quarter second or whatever 1/8 second? It keeps going and going and going. And that's why we use Euler's number, because remember Euler's number was the 1 plus 1/8 plus 1 over 24 plus. It kept going and going and going up into infinity. So that's the reason why we use Euler's number in our formula for continuously compounded interest.